Okay guys, let's take a look at today's lesson. What we're going to be looking at today are applications which use sequences and series. These are some common formulas that we use for sequences and series, and just kind of giving you a heads up. So this formula right here for exponential growth, this formula also works with decay, and I would not give you that formula. You would need to memorize that. So that formula we used last year, we're going to use this year, and we will use also in calculus. So it would be a good idea to have that formula memorized. So the n naught, or whatever variable they're using, it doesn't have to necessarily be an n, stands for the initial population. T is time. Now this is actually a vocab word, relative growth rate. Sometimes in the text of the problem, they'll give you the relative growth rate, and if you don't know what that means, you're not going to really know where it goes. It goes in place of the R, so relative growth rate, and it's expressed as, they usually will describe it as a proportion of the population, like 5% of the population or something like that. The same exact formula can be used for exponential decay. And the only difference is that relative growth rate would be negative on a decay one. That's really the only difference. So it's the same formula. Okay, so they probably don't have this shampoo anymore. The way I memorize this formula is P-E-R-T. P, it was a shampoo called Pert. I know they probably don't have it anymore, but I'm really old, right? So that's how I remember it. The variable could be anything. It doesn't have to be N. It could be P. I mean, it could be really anything. So that's how I memorize it. This one we've also used before, the compounding interest formula, where n is the number of times the interest is compounded annually. You know, like we would say quarterly, we would use a 4, those kind of things, you recall that. The variable up there is this right here. It's kind of hard to see, it's squished together. It's nt. That is nt. So it's n. So we use n twice in the formula actually. We use it as this denominator, and we also use it in the exponent. And T stands for time, and R is the annual interest rate. So there was a question that came up on the daily work. I want to make sure we understand. So this R is an annual interest rate. It's a yearly. If they wanted monthly, we would have to change the units. Right? We couldn't just leave it as a year if they wanted monthly. I don't remember which problem number had that, but that was a big source of confusion for some students. So we would need to change that if they wanted it monthly. And if it's an annual rate and we want it monthly, what would we do to it? Divide by 12, right? We would just divide by 12. That's what we would do to change it to a monthly rate instead of an annual rate. Alright, so I have a variety of, we just have 3 problems actually. There are so many more types of problems, this would be impossible for me to do one of every kind. So I'm just going to kind of do a few of them. The first one, we're going to practice using the exponential growth formula. So we have a median price of a house in Orange County increases by about 6% per year. In 2017, the median price was $440,000. Let P sub n be the median price in years after 2017. Okay, so they want us to find a formula. And they changed the variable on us. Instead of using n, they're wanting us to use P. So P sub n equals, so we're using this formula right here. So our initial condition is 440,000 e to the, we do have the rate. The rate is 6%. I'm going to have to write it as a decimal, so 0.06, and then T stands for time. So that's our formula for that sequence. And using the formula, they want us to find the expected median price in 2027. Now, this is a calculator lesson. So hopefully you have your calculators with you. So let's look and see what we have. They told us that 2017, they're using 2017 as initial. So T would be 0 in 2017. So with that information, that T is 0 in 2017, then we need to figure out what T would be in 2027. So for that, I think it's pretty straightforward. T would be 10. So the value at 10, e to the 0.06 times 10. And we would put that in our calculator and get 801 732 median price for 2027. All right, any questions on that? Okay. Let's go to the next slide. We have a few more examples. We don't get a whole lot of practice with recursive, so I decided to do this number 2. It's requiring a recursive formula, which we know is not the easiest thing for us many times, especially if they want, like, I don't know, this one wants, what, 8 days? After 8 days, so we're going to have to do a little bit of work, but that's what they're asking for. They want a recursive formula, so let's practice. So we have a biologist trying to find optimal salt concentration. She begins with a solution of 4 grams per liters of salt and increases the concentration by 10% each day. So increasing by 10% each day. C naught represents the initial concentration. So C naught would be 4. And C sub n is the concentration after n days. And they want us to do recursive. Okay, so with the recursive, we have to have initial condition or we can't do it, right? Because the recursive builds off of previous information that we have. We can't just go into a recursive definition with no information. So we know that our initial condition is 4. And this, we'll just write that as a pair. So it's 2 pieces to our equation. So C sub n is going to be, let's see, we want to take the previous term, so C to the n minus 1, this means the previous term, so the 4. And let's see, we want it to increase by 10% each day. So if I'm increasing by 10% each day, the quickest, easiest way to do that would be to multiply by 1.1, right? We know why we put the 1 in there, right? The 1.1, so it preserves the principal. So that would be the easiest, quickest way. So we're just going to do that. We're going to multiply by 1.1. And that's my recursive equation that describes this activity. I'm sure we could probably write an explicit equation. It would be much easier for us if we did, but that's just not what they asked for. They asked for recursive. And then they're asking us to find the salt concentration after 8 days. So we would have our calculator. We're just going to do a little bit of work. And I'm just going to log that work in like a chart. So this will be our n, and this will be our C sub n. So when n is 0, we know that the concentration is at 4. And then when n is 1, we would do, so this formula tells me to go back and take n minus 1. So to do my first one, 1 minus 1 is 0. C sub 0 is 4. 4 times 1.1. Okay, we understand how that formula works. We're just going back 4 times 1.1, and that gives us 4.4. And then when n is 2, we do the same thing. We're just going to, it's repetitive. It's recursive. We're just going to keep multiplying by 1.1 until we get to the value that we're looking for. So 4.4 times 1.1 gives us 4.84. And then 4.84 times 1.1 gives us 5.324. And we just keep moving on, multiplying by 1.1. At 4, it's 5.856. At 5, it's 6.442. At 6, it's 7.086. Oh, we're almost there. 7, it's 7.795. And finally, where we're going for is 8. At 8, it's 8.574. So what we have discovered is that the salt concentration after 8 days is 8.574 grams per liter. Excuse me, after 8 days. Okay, and there's just an example using a recursive. Okay, we okay with that? All right, the last one. This is a classic problem. We love those dropping the ball or whatever. The spring, drop the spring and it bounces back, those kind of problems. So we have a ball that's dropped from a height of 80 feet. The elasticity of the ball is such that it rebounds 3/4 of the distance it's fallen. How high does the ball rebound after the 5th bounce? And then find a formula. So the formula that I come up with may be different than the formula that you come up with, and that's okay. We need to arrive at the same answer. So I'm going to explain how I came up with my formula. You could have a different one. It's geometric, right? Because we keep multiplying by 3/4. 3/4. So I know my R is 3/4. I know that. So this starts out at a height of 80, and then it keeps wanting to know the height, how high it rebounds. So that's my focus. I'm starting at an 80. Okay, but what I'm choosing to do is I'm choosing to make that n. Let me explain why. And I'm choosing to start with an n of 1. So if I make this an n of 1, then what have I calculated? I have calculated the first rebound, right? Because 80 times 3/4 would give me the height of the first rebound. So my number 1 means first rebound. That's how I'm writing the formula. Again, you don't have to write it this way. There are other ways. So that means that for my formula, to get the height of the rebound on the fifth bounce, I'm going to put a 5 into my formula, right? Because if I put a 1 in, I get the first bounce. If I put a 2 in, and so forth. So I'm going to put a 5 in my formula. And then that gives me 18.984 feet. Okay, questions on that one? Okay, so this is just a little sampling. You're going to get to, I know it's going to be so exciting, you're going to get to sample many more on the daily work. So let's go ahead and start that.